I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now, I am going to discuss about the single slit diffraction. Of course, since the derivation means to understand the intensity variation and to derive the intensity expression, it takes so much of time and means consumes a lot of space. That's why it is divided into two parts, part 1 and 2. Now, I am going to discuss about the single slit diffraction part 1. So, at the end of this lecture, the student will able to learn the concept of single slit diffraction. This is due to the Fraunhofer diffraction at the single slit, and also the student can derive the intensity formula of the single slit diffraction. Coming to the Fraunhofer diffraction at the single slit. So, this is the single slit. Here, our assumption is this is a rectangular slit whose length is perpendicular to the plane of the paper or the board, and the width of this one is given by small a. A is the width of the slit. From the sideway, the light rays are passing through the slit. Actually, the basic definition of diffraction is the bending of light rays. Bending is a common phenomenon. That's why the light rays will bend. How much they will bend? The angle of deviation is given by theta. So, the light rays are passing through this one. Actually, in case of Fraunhofer diffraction, we need the lens L, or already just it is L2. In between the slit and the screen, there is one lens introduced. Because of the lens, the light rays are focused at the point say P1. Actually, if there is no bending of light, we get the image at the point P. Because of the bending of light, we get the image at the point P1. Anyhow, on the screen at the P1, what kind of intensity pattern we get? Whether we get the maximum intensity or minimum intensity. Actually, as per the definition, when the light is passing through a slit whose width is comparable to the wavelength of light, then the transmitted light will produce alternate maxima and minima. There is a central maximum, next first order maximum, second order, third order, so on. Left side also first order, second order, like that we get. On the screen, the intensity is distributed like this. So, now we are going to analyze this one mathematically. Where do we find the central maximum? Where do we find first order maximum I1? Where do we find the second order maximum I2? Like that, we have to determine how much intensity will be there for each one, and we are going to analyze the intensity mathematically. So, for that one, I am taking a rectangular slit whose width is small a and whose length is perpendicular to the plane of the paper. I am taking from the sideway, the light rays are entering, and because of diffraction, there is a bending of light. The angle of deviation is given by theta. Now, coming to actually due to the point wavefront at the point at O, what is the disturbance? Actually, wave is nothing but disturbance of a particle of a medium. Wave means it is the disturbance of a particle of a medium. Due to the point wavefront, what is the disturbance created at P1? So, that disturbance is given by Y0, say. That Y0 is a sinusoidal wave. It is given by Y0 is equal to A cos omega t, where A is the amplitude. It is in the simple harmonic motion. A is the amplitude. Say it is Y0. Now, due to the small wavefront dx, how much disturbance is created at the point P? That is given by dy, say. Due to point wavefront at O, the disturbance is given by Y0. Due to small element, the disturbance is given by dy. Due to the entire wavefront, how much disturbance is there? We write y is equal to integral dy. So, this is our way of deriving the derivation. Now, coming to due to the small wavefront, what is the wave equation? Y0 is equal to A cos omega t. Due to small element, the disturbance is given by dy, say. How do we write this dy? dy is equal to a into dx. A is the amplitude. Due to small part, the amplitude means the displacement changes. A into dx cos omega t plus some phase difference. Suppose I write the phase difference phi. Cos omega t plus phi, because of the small element there is a phase change also. What is the phase difference? It is given by phi. How do we get the phase difference phi? Actually there is one formula, phi is equal to 2 pi by lambda into path difference delta. So this is the general formula, 2 pi by lambda. What is the path difference? In this one, suppose I just take from here to here, the distance is given by small x and this is the angle theta. Sin theta is equal to opposite by x, then opposite is equal to x sin theta we can write. Actually from this normal, the light rays are having same path, but from starting from this point to this one, there is an extra path difference that is given by x sin theta. Now this x sin theta, 2 pi by lambda into x sin theta we write here. So automatically what is dy? A dx cos omega t plus phi. What is the phase difference? 2 pi by lambda. Delta means that is x sin theta. So this is small disturbance or displacement. I want to get the total displacement due to the entire wavefront. What is the total displacement? Y is equal to integral dy. So same thing is written here. Y is equal to integral dy. What are the integration limits? Actually the width of this one is given by small a. So I just divide this one into minus a by 2 plus a by 2. Automatically the limits are integral minus a by 2 to plus a by 2 dy. So again what is dy? A dx cos omega t plus 2 pi by lambda x sin theta. Same thing is written here. Afterwards, this is of the formula cos a plus b. Cos a plus b means cos a cos b minus sin a sin b. Actually, cos omega t or sin omega t, they are constant terms. I write outside the integration. Therefore, it is equal to a cos omega t integral minus a by 2 to a by 2 cos 2 pi by lambda x sin theta dx minus a sin omega t, written outside integral minus a by 2 to a by 2 sin of something. So like this we are writing. Integrating, actually we know integral sin theta, it is nothing but minus cos theta. Integral cos theta, nothing but sin theta. So if you integrate this one, you will get cos term, cos of something. What are the limits? Suppose minus a by 2 to a by 2. Actually cos is symmetric in between minus x to x. Therefore you substitute the limits, finally you will get this term as 0. So you can solve this one, simply you will get 0. Substitute here something minus or plus 0 you will get here. And integral cos theta, cos nx dx means sin x by n, you will get, substitute the limits minus a by 2 a by 2. Substituting the limits we get y is equal to a into sin pi a sin theta by lambda by pi sin theta by lambda cos omega t. This is of the form y is equal to some a theta cos omega t. Actually it is of the form, it is also in sinusoidal wave, sinusoidal SHM, simple harmonic motion. So initially y naught is equal to a cos omega t due to point source, point wavefront. Due to entire wavefront, what is the resultant displacement? A theta cos omega t. What is the resultant amplitude then? The resultant amplitude is a sin pi a sin theta by lambda by pi sin theta by lambda. Actually if you observe this one, in the numerator there is a term, in the denominator there is no a term. That's why simply I just multiply and divide with a in the numerator and denominator. So a into a, sin of something by something I am getting. It is written as sin beta by beta. A naught small a into sin beta by beta. What is beta? Pi a sin theta by lambda is taken as beta. Finally, I am getting the equation I is equal to I naught sin square beta by beta square. Actually, this is of the form sin square beta by beta. This is actually the resultant amplitude. What is the resultant amplitude? A theta. It is equal to A into small a and sin beta by beta I am getting. Then what is the intensity formula? Intensity mod amplitude square. So, what is the amplitude square then? A into a whole square is taken as I naught into sin square beta by beta square. Therefore, I is equal to I naught sin square beta by beta square. This is the resultant intensity formula. So, what is beta in this one? Pi a sin theta by lambda. Actually, this is the final resultant equation or resultant wave equation we got. Now, we have to analyze this one. Where do we get the maxima? Where do we get the minima? Something like that we have to analyze. In this article, I am just going to derive the intensity derivation. That is why let us actually analyze, means let us write only the wave, means the resultant intensity equation. I is equal to I naught sin square beta by beta square. So, coming to the summary of this one, actually in this article, say we have discussed what is the single slit diffraction, Fraunhofer diffraction due to single slit. Later on, we have determined, we have derived the intensity formula at the single slit. Okay, thank you very much.